Okay, this is active filter design, lecture 30. In the last class, we were looking at additional issues that crop up when two fully differential transconductors are connected to make a fully differential gyrator. These are the connections we would make in order to realize a gyrator, right? And these capacitors represent the integrating capacitors, all right. And we saw that even though there is negative feedback for differential signals, right? For common mode signals, what happens? There is positive feedback simply because as far as common mode signals are concerned, I mean both the nodes are basically the same, and if I yank the input common mode up, the output common mode will tend to go down, and the next transconductor's input common mode is the same as the output common mode of the previous transconductor. So, this forms a positive feedback loop, and the single ended equivalent for the small signal changes in the common mode signals are basically okay. This is the equivalent circuit for as far as okay, and basically to find the loop gain, what would one do? One would break the loop somewhere, yank one side up and go around the loop and see what happens, right? If we did that, this, if I for example pull this, broke the loop there and pull this up by some small signal quantity V, then this current would be some, let me call this capital GM of S times V, where capital GM happens to be, why do I say GM of S? Yeah, so we have to sit and figure out the transconductance of this composite block. Okay, all I'd like to say is that it is not the transconductance of the transistor. All right, and what would you expect the resistance to be? Would you think it would be high or low? We saw that it's a current source, so ideally it should be infinite. In practice, it will be a large number. I mean, in other words, in practice it will be that GM of the transistor times R will be a very large number, and this goes through this impedance RLC, correct? So, what, and this voltage is sensed by the second transistor on the right, and again is converted into a current, okay, and again goes through the same impedance. So, in other words, the loop gain magnitude is simply proportional to, if you find the gain from if we broke the loop here, applied a voltage there and found the voltage here, this would give the magnitude of the gain of one of these amplifiers. Two such identical amplifiers are connected in cascade, and then the loop is closed. So as far as the loop gain magnitude is concerned, it is simply the magnitude of the gain of one of these blocks whole square. Correct? So the loop gain magnitude, which is now a function of frequency, is this Gm of S multiplied by the load impedance. Correct? And the modulus of this. Okay. Yes? Oh, sorry. The square roots. Correct? Now, if you want to ensure absolute stability, right, what do you think you would like to do with this magnitude? I mean, what is, where are the closed loop poles sitting? Pardon? I mean, at the closed loop poles are the roots of 1 minus loop gain in this particular example, because the feedback is positive, that's all. Correct? So if you do not want instability, what is the cleanest thing to do? So if mod loop gain is much smaller than 1 for all frequencies, then you can ensure that the poles are in the, even though there is positive feedback, right, the loop is stable simply because the magnitude of the gain is much smaller than 1. Is that clear? Please note that positive feedback inherently is not a bad thing as long as the loop gain is small. Correct? So, and what do you expect? So, in other words, what would, as a designer, what I would like to do would be to keep Gm of S times ZL of S much smaller than 1 for all frequencies. Correct? Now, how does ZL of S look like? It's simply the impedance of, let me remind you again that this is if this is L and this is C, this is a parallel RLC network. So how does the impedance look like? It's a band pass response, all right. So at 1 by square root LC, the impedance is R. At DC it is 0, at infinity it is 0, so it probably does something like this. Okay. All right. And how does Gm of S look like? What is the general shape you think? At DC? At DC it must be whatever, it must be 1 by, oh I'm sorry, I keep confusing, please, I will call this RE. Okay, I inadvertently used the same R even for the load. Okay, so what is the DC transconductance? Roughly 1 by RE, and that RE, please note, is the output impedance of the tail current source, which in principle is infinity. So at DC one can conclude that the GM is very small or 0. As frequency starts to increase, what happens? The capacitance dominates over there. I mean, the current flowing through the capacitance, parasitic capacitance here dominates over the current that flows through RE. In other words, you can neglect RE in relation to C. So how do you think the transconductance will look like as a function of frequency? If I plot the magnitude, at low frequency it is 0, then at the corner frequency of that R and the C, RE and C, it will begin to go up, right? So, and beyond a certain point at infinity, what is the transconductance? It must reduce to gm of the transistor, because at infinite frequency the capacitor becomes a short, okay, and the transistor is there all by itself. So, the gm, if I plot as a function of frequency, will look qualitatively look like this. You understand? Okay. In fact, there is no, reason why the high slope region should coincide with omega naught. You understand? It qualitatively looks like this. Huh? At high frequency? See, at DC it is 0, that's clear. At infinite frequency it must tend to gm of the transistor, because the capacitor becomes a short. Is that clear? So, it must start from 0, do this, and then eventually go back to saturated gm. Is that clear? Okay. So, which do you think is the problematic region? Okay, if let us consider two cases. If CE tends to 0, or if the parasitic capacitance across the resistor becomes very, very small, what do you think? Is there, what do you think happens? Pardon? Yeah, so how will the curve look like? It will shift. If CE tends to 0, what will happen? It will tend to the left or to the right? Yes, so what will happen? So, CE tending to 0. Is that clear? You understand? Okay. If on the other hand C becomes very large, what do you think will happen? It will go to the left. Okay. And if C tends to infinity, what will happen? It will always be understand. So, it is in our interest to make sure that C is large or C is small. C is small. Why? The gain is simply the load impedance multiplied by the transconductance. So, it is in our best interest to keep CE as small as possible. Correct? And what is the absolute worst case gain? Right? We notice that the gain cannot exceed GM times R, regardless of the value of CE. Okay? If CE happens to be very, very large, then we need to worry about GM times R. And what is R? We saw yesterday that R depends on, to calculate R, what did we say? This was CC, there is some CP, and this has GMP. So, CC and CP. So, what is the lowest value of R? Even if CP tends to 0 or CC tends to infinity, you can never do better than anything lower than. You understand? Okay. So, the gain one needs to plan, the worst case, if GM of the NMOS transistor times 1 over GMP is much smaller than 1, then you are ensured that when you put the gyrator, when you create the gyrator using the two fully differential transconductors, the result is the closed loop system is stable for common mode signals. Okay? And unfortunately, it turns out that, and as we will see going forward, that if GMP is, I mean, what is this telling you? If you want to make the gain very small, you want to make, for a given GMN, you have to, what do you have to do to the, transconductance of the PMOS device? You would like to make GMP much larger. If GMP becomes much larger, it turns out that noise added by the transistor will degrade the noise performance of the transconductor, as we will see going forward. And therefore, even though this is a clean solution to the problem, right, it is not a particularly good one, given that you have to make GMP very large, right. So, the advantage of having a low capacitance, right. So, in other words, if you minimize the amount of parasitic capacitance at this node, okay, that means what does that achieve? You can use a higher value of, a lower value of GMP, because you are now taking advantage of the fact that the transconductance is falling off, okay, from this peak value. Okay. Ideally, if C is 0, then we won't have to worry about this at all, because there is no feedback. You understand? If this was an open circuit, for example, RE was infinity and CE was 0, then if I yank the gate, nothing happens to the drain current, which means that effectively the feedback loop is broken, or there is a positive feedback loop, but the loop gain is 0, right. So, our aim is to try and minimize the loop magnitude of the loop gain as much as possible. So, it is a very good thing to minimize the capacitance at the tail node, right. So, that we can thereby use a smaller value of GMP, which, as we will find out in a couple of moments, affects the noise performance of the transconductor. Is this clear? Okay. All right. And finally, a small minor point regarding implementation. Yesterday, we said one way of putting CC was like this. This is the error amp. Okay. All right. In some situations, it so happens, especially in very high speed designs, that the delay introduced in this buffer is significant. Is not negligible. Ideally, we've very nicely put x1 here, assuming that it's an ideal voltage controlled voltage source, and there's no real there's no delay there. Another thing that one needs to consider is the value of these resistors. Okay. as far as common mode equivalents are concerned, there's, you can think of it like this, okay, and that goes to Cc, and what is that capacitance? Cp1. Okay. If Cc is much larger than Cp1, which one would tend to do, right, then what is the pole due to this RC network? Rx 1 over Rx by 2 times Cp1, correct. So this introduces an extra pole in the feedback loop or more delay. So what can you comment, what comment can you make about the inductance that you see? Yeah, so what this is telling you is that the I mean, this is no longer behaving like a pure resistor, right? This also behaves like an inductor because of the delay associated with the RC network. Because if you yank the common mode at the input of the buffer, the output is not changing instantaneously, which is what would be required in order to realize a resistor. Is that clear? So what do you think? Can you think of a fix for this? One thing, of course, is to put a capacitor across Rx. Okay, what any other fix? What other fixes can you think of? Where the buffer and this are not involved at all. I mean, you could also somebody had suggested this one. I mean, you can do Cc by 2 and Cc by 2, right? As far as common mode is concerned, I mean, now you see that if I yank both the sides up, right, the voltage at the gate of the PMOS transistor rises up instantaneously. However, as we noted before, this has the problem that it now also forms the Cc by 2 now also starts to appear in the differential mode equivalent, okay, and so I mean, see, no, most of the time you will find that there is no free lunch, okay. It's not, I mean, you fix something and then it comes, everything has its own set of problems, okay. But finally, as an engineer, what you have to do is pick the solution with the least risk. Pardon? Yeah, so which is why I said the buffer itself will have finite output impedance, isn't it? Yeah. So you will still have that delay corresponding to 1 over Gm. Does it make sense? Okay. So very often you will find people doing people getting rid of the tail current source. You understand? I mean, see, if you want to get a differential current, there's no particular need to have the tail current source. You can take two common source amplifiers and operate them as two individual units and simply look at the difference between their drain currents, correct? So that circuit will have the same equivalent for both differential and common mode signals. We have seen all this during EC201, correct? So what is what is the advantage of having the tail current source? The tail current source is giving you common mode rejection, okay? And as we all know, the tail current source also needs a minimum voltage across it in order for that tail thing to behave like a current source. Finally, that's being realized using using transistors, correct? So this basically means that a part of the supply voltage is now needed to be dropped across the tail current. So some people say, hey, if the supply voltage is very low and you don't want to waste, within quotes, waste supply, headroom across the current source, why bother with the current source? Why don't you ground this node, correct? Again, as far as differential equivalents are concerned, this is GMVD incrementally, this current is GMVD in the opposite direction. Common mode feedback in principle will fix the common mode voltage at VCM ref, and everything seems quite okay. What is the problem with this now? I mean, for common mode, getting it to be stable for common mode signals is an absolute nightmare, simply because the common mode gain will be very, very high, and the only thing you can do to make the common mode gain small is what? You have to make GMP much larger than, or at least larger than GMN. Does it make sense? Or am I making any sense at all? Palni Rakesh, what is the common mode gain now? No. What is the common mode impedance looking in? What is the input impedance for common mode signals? 1 over GMP. So what is the common mode gain? GMN by GMP. If you want to make this much smaller than 1, and why am I interested in making it much smaller than 1? Why? Why are we interested in keeping the common mode gain less than 1? The only reason we are interested in doing that is we know that this is going to form one part of the gyrator where there is inherent positive feedback for common mode signals, correct? And the one way of avoiding common mode oscillation without ambiguity is to make sure that the loop gain of that positive feedback loop is much smaller than 1, right? The loop gain of that common mode feedback loop is simply the product of the common mode gains of each transconductor. So keeping the loop gain less than 1 in magnitude is equivalent to saying the common mode gain of each one of the transconductors is smaller than 1, correct? And therefore the magnitude of the loop gain is much smaller than 1, and therefore you are okay. No. Yes. So see, as far as this is concerned, differentially what happens? What is the equivalent for differential signals? The gate of the PMOS transistor for differential signals is grounded. Nothing changes on the top. You understand? Only for common mode signals, the only thing that changes is that the common mode gain is now GMN by GMP. Alright. So if GNM by GMP is has to be small, GMP has to be much larger than GNM or GMN, which means that these low transistors will become principal very large, okay, which contribute to parasitics and all this stuff, and most importantly contribute to noise, okay. And as I said, you know, the first, I mean, something that surprises a lot of inexperienced people is, see, I mean, you see, when you design the transconductor, everything looks very nice, phase margin is small, and you know, the step response looks very clean and beautiful, and then you put two of them together and whoa, what happened? The whole thing is oscillating, okay. The reason is that the common mode feedback, the common mode gain of each one of these transconductors is much too high. All right. Is this clear? Okay. That is this thing. So the bottom line is that even though this looks attractive, okay, it's got, in the sense that it can fit in a lower supply voltage than a differential pair based design, okay, we find that it has got its own set of problems which need to be properly addressed. Pardon? No, if there is a common mode, I mean if there is a differential mode output, the common mode loop is dead. No, for differential outputs the bias point will not get affected, isn't it? So next thing to worry about is noise. Okay. When we were discussing dynamic range scaling and all that, I kind of loosely mentioned that the noise of the transconductor is proportional to the noise output current is proportional to 4 kT gm, and that constant of proportionality is some eta. Okay. So we'll see what that eta is all about, and for that I will draw the differential equivalent circuit of the differential pair, and please note that even if there is a tail current source, as far as differential signals are concerned, that source coupled node is ground, correct? And this is coming from where? This is coming from the error amp, and what is the error amp output for differential signals? It is ground. Okay. Okay. All right. So let me actually, before getting into the differential equivalent, I'd like to impress on you the following. Okay. So the error amplifier will have, I mean this whole thing in the green circle will have its own noise sources, right? So the effect of all those noise sources can be represented by a single noise source, okay, in series with an otherwise noiseless error amplifier, correct? So, and please note, the important thing to observe is that this noise source is applied to both these gates. The same noise source is applied to both these gates. Now, if the same noise source is applied to both these gates, the noise current in each of these transistors due to this noise source is the same, right? And these noise currents are going to flow into the same integrating capacitances, causing the same voltage, correct? The same voltage drop, which means differentially they cancel. So in other words, what is the effect of this noise of the error amplifier on differential outputs? There is no effect. That makes sense because this is a common mode noise source. In other words, this noise source is common to both halves, so it shouldn't matter. Is that clear? Okay. Now, what about noise of the tail current source? This will split equally into two halves. and get integrated, and therefore there should be no impact of the common mode noise source either. Clear? Wonderful. So we don't have to worry about these guys. So as far as the differential equivalent is concerned, I just say we need to worry about only these two transistors. Okay. And just like a resistor noise model is, this corresponds to 4 kT R volt square per hertz. Okay. It turns out that a MOS transistor operating in saturation, in other words, it is operating like a incremental voltage controlled current source. You can think of it, the model which comes from device physics, which we are not really interested in going into right now, is, it turns out, it is 8 kT by 3 gm ampere square per hertz. In other words, apart from the drain current, there is also a noise current where the spectral density of the noise current is dependent on the transconductance, which is an incremental parameter, and this 8 kT by 3. Okay. So if you want to think about it in terms of 4 kT gm times eta, what is eta? 2 by 3. Okay. So this noise current, it has a spectral density of 8, so 4 kT eta gm n. Okay. This noise current has a spectral density 4 kT eta gm p. All right. So if I think of this as a transconductor with a transconductance GMN. See, please note that in the incremental equivalent, it is only the NMOS transistor which is being excited by the input voltage. So the incremental signal current coming out is simply GMN times VD, right. In parallel with this current, there is also a noise current, right. If I call this IA and this IB, and if these were deterministic sources, this current would be IA plus IB, correct. So in terms of spectral densities, IN, output noise, IN out is nothing but IA plus IB. So S IN out is nothing but IA and IB are noise sources, noise currents being produced in the NMOS and PMOS transistors. So they are uncorrelated, correct, which means that I can simply add their spectral densities. So SIA plus SIB. So this is nothing but 4 kT eta times GMN plus GMP. Okay. So look at the transconductor. Its transconductance is GMN. Noise spectral density coming out is 8 kT by 3. Let me call this 8 kT by 3 into GMN plus GMP. Okay. Now, why does this make intuitive sense? Please note, what I wish to point out was that the noise spectral density is not proportional to GMN. There is an additional term GMP. Why does that intuitively make sense? This PMOS transistor is injecting noise just like the NMOS. However, the NMOS transistor is also producing a signal component, whereas the PMOS transistor is just producing noise without producing any signal current. So it makes sense that the transconductor noise performance is actually degraded by the PMOS transistor, which is why in the earlier discussion I had indicated that you want to make GMP as small as possible for noise reasons, right? But if you make GMP very small, the common mode gain goes up. Okay, all right, I will continue in the next class.